We will wear your clothes.
Hello, Chris.
Yeah,
Can you hear me?
yeah, I can.
Okay. Take a projection. Okay, can you see the content, the
Yeah,
transition matter? Okay. And in that chapter, they're a little bit complicated, right? And for the content, the first one is about, and we need to know what is the transition model, okay? And after we learn the transition model, we need to learn the transition model complexes and their property. The property like the complexes, the color ions, the ligands, okay?
okay.
And first, look at, okay, first what is the transition metal? Can you recall? Mm,
Transition metals are elements that can form multiple oxidation states.
yeah, and we know the transition metals, the elements with the incomplicated subshell, right?
Yeah,
Uh,
yeah,
okay, and for this in the table, here's the table, okay, and the D, okay, for the D, okay, the D from the Tinania to the Cooper, right?
yeah,
Okay, and here's the zinc, okay, and we know for these two property, these two elements, why they are not called the transition metal. Mm-hmm.
because they have full and empty D block subshell.
Mm-hmm. Okay. And after that, and we know the configuration is like this, right? Okay.
Yeah,
And for the transition metal, and we call the basic definition for the transition metal so are the elements with the incomplete the D, okay, in the D subshell. Okay, and they can form without the form at least one stable ion, right? Okay, at least one stable, understand, with the incomplicated D subshell, right? So this is called the transition metal, okay, understand?
yeah,
Okay, so the keyword is for this one. Okay, can form at least one stable ion, right? Okay, but for this metal, okay, for this zinc, like zinc, right? The only forms like the ions, this type of ions, right?
yeah,
Understand?
yeah,
Okay, and for this, okay, and for the electron configuration, and we know for full electronic configuration of the first D series, for the transition metals, okay, it's like this part, right?
yeah.
From this one to this one, right?
Okay.
Understand?
Yeah,
Okay. For this type of the metals, okay, that we call the transition metal. Okay, here is the element. Okay, understand?
yeah, yeah,
So this row and this column, and we call this is the element, this is the basic element of the transition metal. Okay, and according to the electronic configuration, what we can see, is there any similarity from their electronic configuration?
the D block is getting filled.
Okay, no problem, right?
Yeah,
Understand?
yeah,
Okay, and for this one, here's the work example. And the work example just want us to state the full electronic configuration of this one. This one is what?
manganese 3 plus.
Yes. Okay, so how to state the full electronic configuration? There's a three, manganese. Okay, how to state the full electronic configuration? How's like the full electric configuration is like?
So one S2, two S2, two P6, three S2,
Mhm.
three P6, and
Okay,
four, and then 4S is empty.
so you can reference this one, right?
Yeah,
Understand? No problem.
yeah,
Okay, so the final that we can, because this is the we have the 25 electrons, right? Understand?
okay.
No problem. Okay. And there are some general properties, okay, for transition, on transition. Okay. The difference is like for the transition metals, they have the four property. The first property is the variable oxidation states. Okay. So if the metal is the transition, if the transition elements, the metal, okay, they probably have the variable oxidation states, okay. And second, the form complex ions. And the third is form colored compounds, okay. And
Okay.
final, the fourth one is the behave, maybe a catalyst. Understand?
Okay.
Okay, the four properties, okay, are for the transition metals, okay.
Yeah.
Understand? And other metals maybe not have this property. Okay, understand?
Yeah.
Okay, and the first one property is the variable oxidation number. Okay, how is the variable oxidation number? Mm-hmm. Take for example, for this iron. This iron is what? The ions is what?
2 plus
Is the
and 3
iron?
plus.
Yeah, it's the ferrous, right? Understand?
Yeah. Yeah.
It's the ferrous ions, iron, right? The iron ions. Okay, and this one is what?
3 plus.
Yeah, it's 3 plus. Okay, the 3 plus is the ferric. Okay, it's a ferric. It's a ferric iron ions, right?
How to spell?
It's a ferric. FERRNIC. And the two positive is the ferrous. Ferrous. Understand now?
Okay.
Mm-hmm.
Yeah.
Okay, this one. Okay, and we know and how to the transition metal, the iron that we have the common two types of the ions, right? The first one is the ferrous, first the iron ions. Okay, the second is the three positive is the ferric iron ions, right? Okay, understand?
Okay.
Okay, so you tell me how is the process to forming the ferric, the two positive iron ions, and how to form the another type of the ions, the iron three positive. This one. How's the process?
For 2 plus, the 4s2 subshell loses 2 electrons.
Okay, and for the three plus.
The 3 plus is the 4s2, 2 electrons lost, and then also in
Mm-hmm.
the 3d6 is lose 1 electron and then lose to 3d5.
Okay, and we know when the orbitals are occupied, right? And here's the repulsion between the electrons pushes the 4s into the higher energy state, right? Okay, understand?
Yeah.
Okay, and we know there will be a little bit higher in energy than the 3D subshell, right? Okay, no problem now.
Yeah. Okay. Okay.
Okay, and so here is the table. The table are for the transition element. The transition element, they have the common oxidation state, right? Okay, so for this one is what?
So titanium.
Yeah, for the titanium, we normal, okay, and we normal have the common oxidation state, maybe the three types, right? The first is the positive two, and the positive three, and the positive four, right? Understand?
Yeah.
Okay, and for the nickel, we also have the three types of the oxidation state. Okay, understand?
Okay.
Now, and for this one, it's the iron. Okay, and we previously ignored this iron. Okay, then we have the two, right? The ferrous and the ferric. Understand now?
Yeah. Yeah.
And for the most types of this one is manganese. Manganese have the four, right? Four types of common oxidation state, right? like the positive 2, 4, 6, and 7, right?
Okay.
Okay, and for this of the table, and after we learned the oxidation state, right? And this is the first. Okay, so now you tell me the first property of the transition metal is what for oxidation number? Mm-hmm. For
Property.
transition, how is the oxidation number for the metal? The metal what? What metal? What metal have the oxidation number? And which metal have this oxidation number more than one? Mhm. The oxidation state, the variable oxidation state.
The iron has +2 and +3.
Mm-hmm.
The manganese has 4 oxidation state.
Okay, so the we need you to memorize, right? To memorize the table, right? Okay, the table is for the common oxidation state for the transition element, right? Okay, so if the metal is one of the transition element, okay, and there will be more than one oxidation state, right? Understand?
Yeah.
This is the first property of the transition metal, okay? Understand? And after that, and we're going to know the second property. Okay, the second property is like the complexes. Okay, the for the transition metal, that we have their corresponding complexes. And for the transition metal ions, okay, after we know the oxidation state, and for the transition element ions can form the complexes. Okay, and the constant the essential metal ion or ligands. Okay, understand? How's the ligands? What is the ligands? Ligands like the molecular or the ion that forms a coordinate bond. Okay, and
Yeah.
there is a transition metal by one is the donating a pair of electron to the bond, right? Okay, here's the process the donating a pair of electrons. Okay, understand?
Yeah.
Like the electron pair donor. Okay, no problem. So this
Okay.
is ligand. Okay, so that we call ligand. Okay, and this means the ligand actually have the negative charge or the lone pair of electrons, right? Understand?
Yeah.
Okay, and have the ability to be donated, right? No problem. So and this so in this process is a little bit similar to another process. Another process is what? Mm-hmm. For ligand. Another process is have similar with the ligand. Is what? Is the nucleophile. Okay. So how is the nucleophile? Tell me. What
Nucleophile
is,
donates a pair of electron to the partially positive uh,
yeah.
group or center atom to substitute a group.
Okay, no problem, right? Okay, so this is a little bit have the similarity with the ligand, right?
Yeah.
Actually, okay, and we know the ligand have a capable of being donated, right? Okay, and there is the electron pair donor. Okay, no problem. Okay,
Okay.
okay, and there are different ligands can form actually. The if we have the different ligands can form different numbers of the dative bonds, okay, to the central metal iron. Understand?
Yeah.
Okay, and for this, okay, this one, uh, there are some common ligands, like the water. Look at this one. Okay, this ligand is the water. Okay, and here's the formula of the ligand. Water molecule frequently act as ligands. Okay, and we know the each water molecule will make the single bond, right? They will make the single bond, right? No problem. And the single bond with the metal ion, using one. The one is what? It's lone pair, right? No problem. Mm-hmm. How is the single bond forming in the water?
From the
Think about
oxygen.
it. Okay, because the oxygen, right, has the lone pair on the oxygen atom, right? No
Yeah.
problem. Okay, so this process that forms the forms of the ligand, right, of water. Understand?
Okay.
Okay. Another one is ammonia. Okay. Just tell me how is the process to form a ligand about ammonia? Mm-hmm. Who has the lone pairs?
The nitrogen.
Yes. The added nitrogen, right,
Yeah.
has the lone pair, okay, and makes the single bond, right? Understand?
Yeah.
No problem. And how is this one? Which one?
Cyanide. I think
The cyanide. How's the cyanide?
the carbon donate.
Okay, no problem, right? Understand now.
Yeah.
Okay, and if we want to present the complex ions, okay, and there's some the forms. The forms must includes the square bracket. Understand? There is the square bracket are used to help us to group together the ligands and metal ions, okay? And this one, like this one, understand? Mm-hmm.
Yeah. Okay.
Okay. So if the ligand are neutral, right, and we know the overcharge will be same as the oxidation state of the previous the metal ion. Understand?
Yeah.
Mm-hmm. No problem now.
Yeah, no problem.
Okay. And for this one, another process about the ligand is to name the complexes. Okay, name complexes is a little bit important. Okay, and here's the process how to name the complexes. The first one, that we have to the prefix. Okay, there's the prefix for number of ligands. Okay, or the element or the oxidation number. Okay, and for this one, and you can tell me how's the formula, the chemistry formula for this one.
I don't know what the chlorocuprate is.
What were
The chlorocuprate. I don't know what it is.
this one?
Yeah, in the
Okay,
red.
this one is a salt. A salt that made of the copper,
Okay.
and this one, chloro.
Then what is the formula for the salt?
Okay, the first one, let me explain. The tera represent the four. Okay,
Yeah.
understand? There
Okay.
are four. There are four chloro. Chloro like the ions. This one, the chlorate ions, right?
Yeah.
Okay. And another is the corporate. The corporate is what? The corporate is like this one. It's a Cooper ions, right? Understand
Yeah.
the problem? So
Okay.
combine with this one. The first, okay, the prefix, the first prefix, the tera is representing the four. The number is a four. Okay, the chlora is representing the ions for chlorate, right? Understand?
Yeah.
The Cooper represent the Cooper ions. Understand? Two
Yeah.
plus. Okay, so final the formulas is like this one. So we know there's the 4 chloride, right? And this one, okay? And here's the Cooper, right? Here's the 4, right? And according to that, and how's this one?
It's 2 minus.
2 minus, right?
Yeah.
Understand, no problem. Okay, now think about this one. Hex. Hex represent number is what?
A number
This one?
6.
Yeah, the 6. And how's this one? Where?
Aqua is water, and iron 2 is Fe2 plus.
Yeah, it's water, right? And so here's the square bracket. So it's the iron, right? And the water, right? No problem. Understand?
Yeah.
And here's the 6, right? And how's this is what?
2 plus.
Yeah, no problem. Okay. And for this one, the hex represent what?
Hexa is 6.
Mm-hmm. It's 6, right? Okay.
Yeah.
And another, this one,
Amine is
Amine cobalt is what?
NH3.
Why the 3? Mm-hmm. It's 3, right?
Yeah.
This one. It's this one, right? Ammonia. Okay. So the cobalt is what? Mm-hmm.
CO2 plus.
Is CO, right? Okay.
Yeah.
Okay. So here's the bracket is CO, and here's the ammonia ammonia is the 6, right?
Yeah.
Understand? And this one is what? 2
2
positive,
plus.
right?
2
2
plus.
plus. Okay, no problem. Understand now?
Yeah.
Okay, so how to name the complex? First, here's the prefix. The prefix represents a number, okay, in the organic chemistry. Like the D is for 2, right?
Yeah.
Okay. The tetra represent this 4, okay, and hex represent the 6, okay. And for the respect of the 3 and 5, 5 rarely encounter, right? Understand?
Yeah.
Okay, no problem now.
No problem.
Okay, okay. And here's and I know the Cooper is an nickel part, representing the place of the Cooper and the nickel. Understand this one? Mm-hmm. No problem.
Okay.
Okay. And for this one, ammonia. Ammonia will take the prefix amine, right? As the ligand, which is spelled a double. Understand? No problem
Okay.
now.
Okay. Yeah.
And okay, this is the second. Okay, after that, we have learned the 2 property of the transition. Okay, of the transition method. Okay, so now you tell me the first property is what, and the second property is what?
First property, multiple oxidation states.
Mm-hmm. And the second property is what? The second property is what?
Can act as catalyst.
To complex, right?
Oh, complex.
Yeah, complex. Okay, the complex is forming ligand, right?
Yeah.
Understand?
Yeah.
Okay. And here's the third property. The third property is related to the color. Okay, and we know there are colored ions. Okay, okay, understand. And here. Okay, here's the wheel. Okay, the wheel record different colors. Okay, and look at that. And we know most transition metal compounds appear colored. This is because they will observe. They will observe what? Mm-hmm.
The light.
Observe what? absorb energy.
Yeah.
Understand?
Yeah.
Absorb energy, and according to what? According to the certain parts of the visible electromagnetic spectrum, right? And we know the color. Here's the color of the wheel. Okay, this one. Mm-hmm.
Yeah.
Okay, and we know if the green, and here's the complementary is red, right?
Yeah.
Okay, and here's the color absorbed are complementary to the color absorbed. Okay, just like if one color is green, okay, if here's the green compound, will absorb all frequencies of the spectrum apart from the green light, right? And the color is transmitted, right? Understand? No problem now. Okay, and for this wheel, okay, this wheel, this wheel, and shoot all of the colors, okay, in the visible line, okay, of the electromagnetic spectrum. No problem.
Yeah.
Okay, and after that, and here we know, and after we know the complementary colors, are any two colors which are directly opposite each other in the color wheel. Okay, and for example, the complementary color of red is green, and complementary colors of red violet are yellow green. Understand? Look at the graph, the wheel. Mm-hmm. And tell me, how's the complementary of the red? When of the red is green, and the
Yeah.
complementary of the red violet is yellow green. Is that right?
Yeah.
Okay, no problem now.
No problem.
Okay, and after that, there is the splitting. There's a splitting of the 3D energy level. Okay, the energy level is like the we will learn in the fixed lesson, and the energy level is same as the fixed lesson. The energy level is like if we want to emit electron, right? And here's the energy level. We'll emit it or absorb energy, right? Understand? No problem. The energy level. Okay, understand.
Yeah.
Okay, and for this one. And we know for the transition metal atom, and we know there are five orbitals, right? The makeup of the d subshell, right? And may have the same energy, right? Because the same subshell, right, have the same energy. Okay, and if the one ion that have the completely feel the 3D energy level, like the ions of zinc, right? Okay, and for another ion that have no electrons in the 3D subshell, right? And are not colored. Understand?
Yeah.
The problem?
No problem.
Okay, and we know the transition metal have the partial field 3D energy level. Okay, and if one of and we know if the one of the electrons in the lower energy level, and if the electrons absorb the energy from the visible spectrum, right? And they can go the higher energy level, right? And in this process, the from the lower level to higher level, the process that we call the promotion or the excited, right? Excitation, right? Understand? No problem.
Okay.
Okay, from a lower energy level and to the higher energy level. Okay, and this process that we call excitation, right?
Yeah.
Okay, and the spectrum that we call the absorption spectrum. Okay,
Yeah. Yeah.
problem. Okay, and the amount of energy observed what depends on actually the energy level difference, right? Okay, no problem.
Yeah. No problem.
Okay, and if we want if the next section is the changes in the color. Okay, and if after we know the size of the splitting energy, the delta E, the energy level difference. Okay, and if there one is the d orbital. Okay, orbital is influenced by the following four factors. Okay, and the size and type, the ligand, right?
Yeah.
Understand the
Okay.
factors. Okay, and the second is the nuclear charge and the identity of the metal ion. Okay, And
Okay.
the third factors is for the oxidation state of the metal. And the next one is the shape of the complex. No problem.
Shape. Yeah. Okay.
So which the four factors? Okay, the four factors that will change the color, right? Okay, understand. So why is the color different? Because there are four factors, okay? Maybe the size and the type of ligands, or maybe the nuclear charge or the identity of the metal ion. The one of the factors may produce the different color, right? Understand? So these four are the main reason for the changing in the color, okay? Understand?
Yeah.
And for this one, okay, and you can see from the graph, okay, they are different colors, right? Okay, maybe they have the different ions, right? Make different shape, right? Make different ligands, right? Understand?
Yeah.
No problem. Okay, so the four factors, okay, that we need to memorize, okay. And for another one is the size and type of ligand, okay, and the size and type of ligand, and we know the nature of the ligand actually will influence the strength of the interaction between the ligand and the central metal ion. Okay, understand?
Yeah.
And we know the ligand actually vary in their charge density, right? No problem. Understand?
How, how is how does the charge density change here?
Which part? You don't
The charge
understand?
density.
The charge density, right?
Yeah. How
Because
does it change?
because when if the size and type of ligand different, right, and they have the different charge density. Understand?
The charge density is the size, the charge over size.
Mm-hmm.
Oh, okay.
Actually, for the ligands vary in their charge density. Okay, first we need to know what is the charge density. Mm-hmm.
It's the charge
Actually,
over.
actually, the charge density refers to the ratio of the ligand's charge to their volume, right?
Yeah, yeah.
Understand? Okay, and we know that if there are different ligands, actually have the different charge density. The reason is that if they carry different amounts of electron charge, right? Understand? Mm-hmm. This one. Mm-hmm.
Yeah.
It's like, for example, if like this, think about it, this one. Okay, the charge is different, right? Is this a negative? Okay, and if I give the think about it, the neutral ligand, like ammonia, no problem. Mm-hmm. This one, the ammonia have no charge, right?
Yeah.
This one's negative, right? This one's negative, okay. And if they carry different amounts of the electric charge, okay, they may produce the different charge density, right? Okay, understand?
Okay. Yeah.
Okay. Or another reason, maybe if they have the different size or different radius, okay. If they have different radius, will produce different volume, right? Okay. If they have the different volume, okay, then maybe the charge density changes, right? Understand? No problem.
Which radius is it? Is the radius of the whole molecule or the radius of the atom with the charge?
Mm, the atom with charge,
Okay.
no problem.
Yeah.
Okay. And another is so if the greater charge density, right? Okay, and we know they're more strongly the ligand interact with the metal ion, okay, and thus which will cause the greater splitting of the d orbitals. Okay. And we also know if there's the greater the splitting, the more energy needed to promote an electron to the higher group of orbitals.
Yeah.
Okay, no problem. And the fifth one is that if the further if the further it is shifted to virtual region of the spectrum where it observes the higher energy. Okay, understand? No problem.
Okay.
Understand now?
Yeah.
Okay, and here's the conclusion. So a different color of light is observed by the complex solution, and the different complementary colors observed. Okay, and which means the complexes with the same transition. Okay, transition element ions, but different ligands can have the different colors. No problem now. No problem now.
Yeah.
Okay. And for this one, for example, okay, and this one, why the complexes have the light blue color? Mm-hmm. And this one,
Because the complement's color is removed.
okay, understand now.
Yeah.
And whereas this one is a dark blue, okay, no problem. Because we have the oxidation in the state of the positive two, right?
Yeah.
Okay, positive two in both complexes. Okay, understand. And for this one, okay, here's the color, right? Why the color differs? Okay, and this is the oxidation number. So when the same metal has the higher oxidation number, that will also create the strong interaction with the ligands. Okay, so if you want to compare the iron and iron, okay, and they will absorb in the red region and appears green. Okay, no problem now. This one, understand? No problem.
Okay. 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 Yeah.
Is there any problem?
No problem.
Okay, and next one is the coordination number. Okay, and we know if the change of the color in complex is also partly due to the change in the coordination number and the geometry of the complex I. Okay, after we learned the splitting energy is related to the energy level difference, right? Okay, and they will affect by the relative orientation of the ligand as well as the d orbitals. Okay, no problem. No problem now. So
Yeah.
if we change the coordination number, they generally involve changing the line as well. So it is the combination of these factors, the orders, the strength of the interaction. Understand now? No problem now.
No problem.
Mhm. Okay. Okay. And for this one, okay, this one is for after that we have learned the four factors. Okay. Understand now?
Okay. Okay. Yeah.
These are the four. Okay. Let's re quick review this one. Therefore, okay, this one. Mm, this one. Okay. After that, we have learned the three property, right? Understand?
Yeah.
Okay. In the previous pages that we have learned the first property is variable oxidation state, and second is formal complex ions, and third is formal color compounds. Okay. And after that, we have to learn another. After that is the color, and another is this fourth. This one. Okay, this one is monodentate. Okay, what is the monodentate ligands? Okay, actually, the monodentate ligands can form only one dative bond. Okay, there is the only one dative bond to the central metal. Okay, so this
Okay.
is we call the monodentate. Okay, this is the monodentate ligands. Okay, because there is the only one dative bond forming. Okay, understand?
Yeah.
Actually, there's only one single lone pair of electrons to form a dative bond with the metal ion, right?
Yeah.
Understand?
Okay.
Okay, if there is more than one, then we call it the multidentate ligand. Okay,
Yeah.
understand?
Okay.
Okay, here's the examples. Here's three examples. First is like water. Okay, so tell me, how's the water? Why water is the monodentate ligand?
Because only one pair of electrons is donated from the oxygen atom to the center metal.
Okay, no problem now. Okay, understand.
Yeah.
Mm-hmm. Okay, and next one is the bidentate, right? Or the multiple, right? The which means that there are more than one, right? Or maybe the two dative bonds, right? Okay, the bidentate ligand is actually the forms or forming of two dative bonds to the central metal ion, right? Okay, understand? Actually, there contains two atoms with the one pair of the electrons. Okay, and look at the example, this one. Okay, use this example and tell me why there's two dative bonds and why we contains two atoms with one pairs of electrons. Mm-hmm. Think about
Because there's two nitrogen atom.
it. Okay, no problem.
Yeah.
Okay, like this graph. Mm-hmm. Okay, understand now.
Okay.
Look
Yeah.
at the
Yeah.
graph. Okay,
Yeah.
and after that, the bidentate, and the next one is the multidentate ligands. Multidentate actually there will be more than there will be more dative bonds, right? And then the two dative, right? Okay, and there like this the graph. Look at the graph. Okay, this graph. Okay, here the graph actually is the multidentate ligands, right? Okay, and we use which axis is the hex. Actually, it's the hex, right? Why there's the hex dentate? Why there's the hex dentate? Mm-hmm.
Is the six
Hex is
donated?
yeah. Hex actually represent the number six, right? So there are six dative covalent bond, right? Where is the six?
Four
Mm-hmm.
on the oxygen and two on the nitrogen.
Okay, no problem now.
Yeah.
Okay, so this is called the multidentate ligands. Okay, and after that is the alkyl. Okay, this one is another type of the complexes. Okay, the number octa represent what? Represent number what? Mm-hmm.
Eight. Said
Octahedral
eight.
is the A, right? No problem. Okay,
Okay.
understand.
Yeah.
Okay, and so and for that, here's an example. Example such ligands are water ammonia molecule, right? And hydroxide, right? Understand? Look at the table. The table. Okay, so if there are six ligands, okay, these complexes are some described that have the six for the coordination, right? Understand? No problem. Understand now?
Yeah.
Okay. Look at graph. Okay. No problem. The, is there any problem?
No. No. No.
Okay. Okay. Look at graph. Here's a graph. Okay. The number of the The ligands is what? Is what? Mm-hmm. The bonds is what? The left graph, a bond.
Is bidentate and then it's octahedral.
Okay, no problem. How's the right?
Is also the same.
Okay, no problem now.
Yeah.
Mm-hmm. And for next one actually another example of the octahedral complex with the bidentate ligands. Okay, okay, and here is the multidentate ligand. Okay, according to the multidentate ligand, okay, there is a number of bonds is what? Mm-hmm.
Is six coordination bond.
Okay, no problem now.
Yeah.
Okay, and according to their angle, okay, the bond angles, okay, is 90. Okay, and for the coordination number of the complex is the number of the dative bonds formed between the central metal ion and the ligands. Okay,
Yeah.
no problem. And we know there actually are six dative bonds. The coordination number of the complex is six. Understand? No problem now.
Yeah.
Okay. And for next one, okay, this represent the number is what?
Four.
Is it four, right?
Yeah.
Okay. And according to the four, and we know the angle between every bond is what?
100, 109.5.
Yes, no problem. Understand?
Yeah.
Okay. And this form that we call the tetrahedral complexes, right? Actually there are four coordinate bonds, right? Okay, and the angle between every single bond is the 109.5, right? The angle. Understand?
Yeah.
Okay, and according to a graph, and we know the the central metal is the copper, right?
Yeah.
Okay, and for this one, okay, this one is the cis and platinum. Okay, and the cis and platinum represent what? Actually, the complexes with the four, if there are four coordinate bonds, okay, may adopt a square planar. Okay, look at graph. Okay, this is a square planar. Okay, the geometry is the square planar. Okay, not the tetrahedral, right?
Yeah.
Okay, it's the planar. Okay, it's planar geometry. Okay, and according to this, and this form that we call the cisplatin. Okay, this is square planar complex is the cisplatin. Understand now?
Okay.
No problem. No problem now.
Yeah.
Okay, and according to the graph, this is a cis and this is a trans. Okay, tell me, what is the difference between the cis and trans ladder? Mm-hmm.
For the cis, the groups are on the same side. For the trans, the groups are in the opposite side.
Okay, no problem now.
Yeah.
Okay, and according to that, this planar molecular, no, this planar molecular, okay, for this type of the usage, here is a usage, okay? The usage is, and we know the cancer cell, okay, can grow and replicate, right? Much faster than a normal cell, okay? And we know the drug for this one, the drug, okay, the drug cisplatin was discovered, right? And there's the usage, okay, usage for what? For treating a number of different types of cancers, right? Understand? This type of the cancers, right? Okay, that we can use the drug, the cisplatin to cover it. Understand? To treat that.
Okay.
No problem.
Yeah.
Okay, understand now?
Yeah. Yeah.
Okay, and we know the cisplatin works by the by con by binding the nitrogen atom on the base. Okay, actually, this is the actual process. A process how is the principle of the cisplatin. Okay, the first step is the cisplatin works by binding the nitrogen atom on the bases in DNA. Okay, and second, the cisplatin passes through the cell membrane. Okay, and undergoes the ligand exchange. And in the process, and we know the chlorine are replaced by the water molecules. Okay, understand? Remember the every single step. Okay, okay, no problem. And the nitrogen is a better ligand than water. Okay, and I want to know what is nitrogen is better ligand than water.
Because it's
Will form what?
because the nitrogen can more easily lose the electrons.
Lose what?
Lose the electron.
Okay, actually, and we know, uh, in the process of the forms the dative covalent bond, right? With the cisplatin, right? Okay, the nitrogen is the better. It's better lose, right? Understand? No problem.
Yeah.
Okay. And fourth one is the cisplatin will distort the shape of the DNA, okay, and prevent the DNA from replicating. Understand? Okay. This is the basic principle. Understand the cisplatin. Okay. No problem now. Mm-hmm. Understand. Hello, can you hear me?
Said I can understand.
You can't understand, right?
Yeah, can.
Oh, you can understand, right?
Yeah.
Okay. And here's the beta graph of the process. Look at that. The first step, the second step, and third step, and fourth step. Okay, no problem. Actually, this is the mechanism of action of the cisplatin. Understand? No problem.
Okay.
Mhm. The mechanism of the action of the cisplatin divided the four steps. First step is like this one. Is like the cellular uptake. Okay. The second is like the ligand exchange, right? Okay. And the third one is the DNA binding. Okay. And the final one is like the DNA damage. Okay. DNA damage or replication inhabiting. Understand?
Yeah.
Okay. So remember the mechanism of action of the cisplatin. No problem now.
No problem.
Okay. And after that, remember there also have some adverse effects. Okay. This one. The first is it's it binds to healthy cells. Okay, also, okay. The second, okay, there are other healthy cells are replicate quickly, okay. Understand? And the third one, there will hair loss. Okay. And the fourth one, there's the drawback. The drawback is the balance. There's the balance between adverse effect drugs and their value, theoretical value. Understand?
Okay.
Okay. And for another one, this one. Okay. And in the process we called hemoglobin is one of the nature of complexes used in a transition metal. Okay, understand?
Yeah, okay.
Okay, and according to the graph, you can see the iron. Okay, the iron is in the center. Okay, no problem.
Yeah.
Okay, and this is actually is the protein, right? It's protein. Okay, this one. Mm-hmm. Okay, the function for this hemoglobin is one of the nature's complexes used in the transition. The the metal iron, right? The iron, right?
Yeah.
Understand? Okay, and the core actually is the iron, the 2+, right? Understand?
Okay.
Mm-hmm. Okay, and according to that, there's the fifth dative bond from the protein. Okay, no problem now.
Where's the fifth? Where is it? The five dative bond.
Okay, and we know there is the fifth dative to produce to form to form.
But on the diagram, there's none. On the
Why?
diagram is four. On the diagram is four. Why is there five?
The fifth, right?
Yeah.
Okay, according to the graph, we can see in the structure. Okay, in the structure, there will actually there only forms. You are right. The only forms the four dative covalent bond, right? Okay, there
Yeah.
in the graph, the only forms the four dative covalent bonds with the this one the nitrogen atoms. Okay, from the group, right? In the square planar arrangement, and the word is for the fifth dative. The fifth dative is formed when the proton or part of this donates. Okay, so when the fifth dative covalent bond is formed, when this proton the the globin will donate. It's when it donates a lone pair of electrons into the empty orbital. Okay, and in this process there will a fifth dative covalent bond, right? Understand now?
Yeah.
Mm-hmm.
All right.
Hello?
Yeah. Yeah.
Can you understand? Okay, so according to the graph, actually, there are only four dative covalent bonds with the nitrogen atoms from the Hem group, right? In the square planar arrangement. Okay, and for this word, this sentence, the fifth dative bond is formed when the globin is the globin the globin is the protein part of the hemoglobin, right?
Yeah.
Donates if they donate a known pair of the electrons into the empty, okay, into an empty orbital, okay, of the iron 2+ iron, okay, and there's the bond, okay, there's a bond anchors the Hem group to the globin protein, right? Understand? Understand now? Mm-hmm. I
Yeah.
can hear. Okay, no problem now.
Yeah.
Okay, and so the process actually the oxygen molecule are not very good ligands. Okay, okay, understand? To vacancy of the iron 2+, right? No problem.
Okay. Yeah.
Okay, and at the same time, the weak bonds allow stain to break off easily and be transported into cells. Okay, and here's the detailed process. Okay, no problem now.
Okay. No problem.
Okay. And another another for this one. Okay. This one is the fourth property. What? The transition metal. Okay. The fourth property is for the catalyst. What is a catalyst or the catalysis?
It provides a lower activation energy.
Okay, no problem. Okay. And we know for the transition metals are often used as a catalyst in the element form or the compound. Okay.
Yeah,
And we know the ability of a transition metal will form more than the one stable oxidation state, which means they can accept or lose it actually lose electrons, okay, or accept or lose electrons easily, okay, and so they can be the catalyst, right? Understand? Okay, and for the catalyst, there are two types. The first type is the heater. Okay, what is a heater? This one.
hetero is the different state.
Okay, it's different state. Okay, understand?
Yeah,
Okay, like this form, right? Okay, how is the HOMO? HOMO is the same, right?
yeah, same.
Okay, it's the same. It's the same as the reactant, right? Okay, no problem. No crack.
Yeah, no problem.
Okay, and for the heterogeneous catalyst, okay, for the hetero catalyst is a different physical state, okay, from the reactant. Okay, and the heterogeneous catalysts are unisolid. Okay, understand? And for the surface, okay, there are first is absorption and the second reaction, and the third one is the deportion, right? Dispersion, right?
Okay.
No problem. Okay, and another is the strength. Okay, the strength for this is for it actually will help to determine the effectiveness of the catalyst activity. Understand? And the
Yeah,
second is the surface area, and remember the advantage of this one. Okay, and the heterogeneous catalysts can be filtered off and are easily separate from the liquid or gaseous products. Okay, no problem. Understand
okay.
now?
Yeah,
Mm-hmm. And for the contact process, okay, no problem. The equation, mm-hmm. The property, the contact process. This is the final step. Is there any problem?
it's okay.
Okay. And how is the catalyst converse works? Okay, look at graph. Okay, catalyst converter are used exhaust boxes to reduce the air pollution. Okay, understand the graph. It's like this. No problem.
Yeah, okay.
Okay, and here is the detailed process. Okay, understand. So this chapter is done. This chapter is totally related to the transition transition metal. Okay,
Okay.
and later I will send this to you. Okay, and after the class you need to take a review. Okay, and reviewing every single content of the little section, right?
Yeah,
Mm-hmm. There are a lot to memorize. Okay,
yeah.
no problem. Is there any problem?
No, no, no. There's no.
Okay, and the next lesson we are going to talk about the neutralization. Okay,
Okay.
titration. The titration. Okay,
Yeah.
okay. So the lesson is over.
Okay. Yeah. Thank
Okay,
you.
bye bye.
Bye bye. As the probe moves away from the comet, the gravitational field strength decreases gradually, therefore the deceleration of the probe decreases as it rises, so it loses speed more slowly and reaches a greater maximum height than calculated. Yes. 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 Changing flux induces tiny electric currents in the disk. Lenses allow the currents create their own magnetic field that opposes the change that causes. Testing, testing. Ah, 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 ah. OBS is using my freaking computer mic instead of my actual mic. Testing now. Testing, testing. Ah, ah. Okay, this is much better. This is what I wanted. The magnetic field and the disk's induced field interact. Turning force. The disk turns in the same direction as the magnet, so the change in flux becomes less. The disk is trying to keep up with the magnet. The spinning magnet drags the disk around without touching it. The disk makes currents that try to stop the change. The easiest way is to spin along.
Graph the transfer six of physics. Okay. Okay. Look at the watch. You're right.
Ah, time to rest a bit and then I'll come back. All right, I'm back, and we're going to follow this to-do list. I'm going to finish everything by the end of the day. I don't think I'm going to have time to finish the physics and math paper, but we can do the corrections and then review today's chemistry lesson, do 6 questions on transition metals, and then do more physics questions. And then after that, and then I also have 2 questions each of topics of chemistry, so I gotta be really efficient today to be able to finish all of this. If I actually finish all of this, then holy shit, that's a miracle, and I should be really proud of myself and then get a good night's sleep. But if I can't, it's okay, because this amount of work is crazy. I don't even know if I can finish these, and this is on top of everything else. This is 8 questions. 8 questions is like 3 hours of work, man. And these are probably gonna take me 4 hours. So like that's already 7 hours, and then I gotta go through I don't want to check that. I gotta also go everything here. So no time to waste, let's get to it. Review physics lesson. We've got the physics lesson right here. So let's close the chat, and then I don't have, maybe I can have subtitles if I refresh. No, it's too long. Okay.
The paper of physics, okay? Okay. What kind of watch? You're right. No problem. Answer
Scalar
C.
quantity.
And the third one is the or and it's the ampere. A, no problem, no. The next X is the hardened, okay, right. And 7 is the no problem, and A is this.
Did he just skip
It's
that
the
one?
hardened, okay, right. And 7
Oh, he ticked
is the
it.
problem, and A is the C. Oh, okay. Here's the problem. You use the conservation, okay, for the unit transfer, okay. And in the topic, okay, the problem has a mass, okay. And now, and we want to know to show the conversion of this mass. You can see the VGE voltage over C squared.
G over voltage C squared.
Why you choose the option 8? Why you choose option 8? Hello?
I think that because convert into energy first.
Yeah. And
so
then
so M equals E over C squared.
First you use the formula of the mass energy, right? The MC squared, okay? This formula, right?
Yeah.
Okay. And according to the mass of the proton, okay, and we take into the equation and we can transfer the energy, right? The energy, the unit is joule, right?
Yeah.
Okay. And 1.67 and times the 10 and that's 27 and times the light speed square, okay? Times the 10 and square, okay? And the first transfer the energy into the what? The joules, right? Into the E voltage, right? The GE voltage, right? Understand? Okay. How to transfer the energy of the joules into the electron voltage? How to transfer? Remember that on the notebook, there's the graph, the transfer. How to transfer? Is it time, or is it multiply or the over?
I forgot, is 1.6 times 10 to negative 19 joules equals 1 electron volt.
Okay, and here's the unit of the G. The G represent what? The G represent
what? Times 10 to the 9. So
no problem. Okay,
yeah.
so the electron voltage, right? So becomes what? And we
Base 44 super agents. Careful, there's no going back. No setup. Just
imagine being able to build an app with your name on it just by thinking about it. Meet Base.
Now, before we talk about how to convert electron volts to joules, let's talk about what an electron volt is. Electron volts is basically a unit of energy, and it relates to the electron. So let's say if we have 2 plates, and let's say this is a negatively charged plate, and this is a positively charged plate. And these 2 plates differ by 1 volt. So let's say this is at 0 volts and this is at 1 volt. The energy acquired by a single electron as it moves through a potential difference of 1 volt, that energy is equal to the electron volt. The electric potential energy is basically equal to the product of the charge times the electric potential in volts. So the magnitude of the charge of an electron is 1.6 times 10 to the negative 19 coulombs. And in this example, we have a potential difference of 1 volt. 1 volt is equal to 1 joule per coulomb. So in this case, the coulombs cancel. So for an electron that moves through a potential difference of 1 volt, it's going to acquire 1.6 times 10 to the negative 19 joules. And so that's equal to an electron volt. So that's how much energy an electron acquires if it moves through a potential of 1 volt. And so now you know the relationship between electron volts and joules. Now, I do want to mention something important. As this electron moves from the negatively charged plate towards the higher, more positively charged plate, it gains 1 electron volt of kinetic energy. So the kinetic energy of the molecule increases. However, the potential energy, that is the electric potential energy, decreases. It loses 1 electron volt. So the mechanical energy of the electron does not change. So keep that in mind. The electric force, which is, the electric field is directed this way, but the electron feels an electric force opposite to the direction of the electric field. The electric force is a conservative force, and therefore it doesn't change the mechanical energy of a charged particle. So whenever a charged particle moves in the direction of an electric field or opposite to the direction of the electric field, the kinetic and the potential energies of that charged particle will change, but the mechanical energy is the same. So in this case, as the kinetic energy of the electron increases by 1 electron volt as it moves from this plate to that plate, the electric potential energy decreases by that same amount, and so the mechanical energy of the electron is conserved. Now let's talk about how to convert electron volts to joules. So as mentioned before, 1 electron volt is 1.6 times 10 to the negative 19 joules. So start with what you're given, 250 electron volts. I'm going to put the unit 1 electron volt on the bottom, and on the top, I'm going to put this. So these two will cancel, and then it's simply going to be 250 times 1.6 times 10 to the negative 19. So in this example, it's 4 times 10 to the negative 17 joules. So that's a simple way in which you can convert electron volts to joules. Now let's say if we have this value, 4 times 10 to the negative 18 joules. How can we convert this to electron volts? Go ahead and try this problem. So we need to start with what we're given, and then use the same conversion. There's 1.6 times 10 to the negative 19 joules per electron volt. And so set it up in such a way that the unit joules cancel, leaving behind electron volts. So this time, we need to divide. And so this turns out to be 25 electron volts. So what this means is that 1 electron would have a voltage of 25 volts. So let's say if there were 2 electrons, it would have a voltage of 12.5 volts. That means each electron would have a voltage of 12.5 volts. So the total energy would be 25 electron volts. If there were 5 electrons, each would have a voltage of 5 volts for a total energy of 25 electron volts. So let's say if we have an of a voltage of 5 volts for a total energy of 25 electron volts. So let's say if we have an energy value of 100 electron volts. So 1 electron with this energy would have a potential of 100 volts. 2 electrons would each have a potential of 50. So 50 plus 50 would be 100. 4 electrons would each have a voltage of 25. 10 electrons would each have a voltage of 10 volts. So hopefully this gives you a better understanding of electron volts. So as you increase the number of electrons, the voltage on each electron decreases so that they can have the same energy. So to calculate the electron volts, or the number of electron volts, you can multiply the number of electrons that you have by the voltage on each. So let's say if there's 40 electrons, and each electron has 50 volts. So the energy, the total energy of these 40 electrons will be 40 times 50. And so that's going to be 2,000 electron volts. Let's calculate it with this equation. So Q would represent the charge of 1 electron, which is 1.6 times 10 to the negative 19. And let's not worry about the negative sign, even though it's supposed to be negative. And it's supposed to be coulombs. I put joules for some reason. So that's the charge of 1 electron. So since we're dealing with 40 electrons, we're going to multiply by 40. And each electron has a voltage of 50 volts. So that's going to be 50 joules per coulomb. So that's the energy of each electron per charge.
这应该是好久以前小时候会的。
现在都忘了，没事，谁也不忘。
Or per unit charge. So it's 40 times 1.6 times 10 to the negative 19 times 50. And so this is going to be 3.2 times 10 to the negative 16 joules. Now, if we want to convert joules back to electron volts, we would have to divide it by 1.6. Times 10 to the negative 19. And this will give us 2,000 electron volts. So you can think of this value as being the number of electrons multiplied by the voltage on each electron.
This game, you're not ready for it.
So let's say if you have a group of electrons, and the total energy is 5,000 electron volts. If each electron has a voltage of 20 volts, how many electrons are there? So what's the number of electrons?
好久以前买的。
Present. So let's see if we can come up with a formula. So the energy in electron volts is going to be equal to the number of electrons, all right, N sub E times the voltage of each electron. So let's put V for volts. So the total energy is 5,000 electron volts. We're looking for the number of electrons, and each electron is 20 volts. So it's going to be 5,000 divided by 20. And so the number of electrons is 250. Here's another question for you. If 80 electrons travel through a potential difference of 500 volts, what is the potential energy change in electron volts? And what is the change in the kinetic energy in electron volts? the change in potential energy is equal to negative Q delta V. Now in this case, we can think of the electrons as being proportional to Q, because charge is proportional to the number of charged particles. So 80 electrons will have a charge of 80 times E, where E is 1.6 times 10 to the negative 19, but technically negative 1.6 times 10 to the negative 19. Now the change in voltage, which is the potential difference, that's going to be 500 volts. So negative 80 times 500, so this is going to be negative 40,000 electron volts. So that's going to be the potential energy change in electron volts as the electrons move towards a high potential. So if the potential energy decreases by that amount, then we should expect that the change in kinetic energy should increase by that amount. So it's going to increase by 40,000 electron volts. And so you could use this formula instead of the other formula I gave to calculate the energy in electron volts if you have the number of electrons and also the potential difference or the voltage of the electrons as they travel from one point to another.
In this video, we're going to convert 1 kilogram into these strange new units, mega electron volts per c squared. And these are very common to use when we're doing nuclear physics calculations. So where this comes from is the famous equation E equals mc squared for the energy equivalence of a mass. And we could also solve this for m. M equals E over c squared, and we'll use both forms of the equation as we do this conversion. So we start out by finding what's the energy equivalence of 1 kilogram of mass, and we plug in c squared, and c is the speed of light, approximately 3 times 10 to the 8th meters per second. And when we run the numbers on this, we get 9 times 10 to the 16 joules. Next, we're going to convert those joules into mega electron volts. And we remember that 1 electron volt, that's the energy of 1 electron passing through a 1 volt potential difference, is 1.6 times 10 to the negative 19 joules. And then mega, of course, means a factor of a million. So 1 mega electron volt for every 10 to the 6th electron volts. And we find our energy equivalence of a 1 kilogram mass is 5.625 times 10 to the 29th mega electron volts. Finally, we go back to E equals mc squared solved for m, and we can express our mass of 1 kilogram as its energy equivalent, 5.625 times 10 to the 29th mega electron volts divided by c squared. And we've got the mass of 1 kilogram written in MeV per c squared. If you find the physics content on Zach's lab,
we know 1G electron voltage, right, equal what? 1.6 and times the 10 and negative 10, right? Joules, right?
Yeah.
Okay, and if I want to transfer the energy of the joules into the GE voltage, okay, so we can what? Use the joules, right, to over, not multiply, understand? So I use the result, this joules, okay, and times the light speed to what? To over, right? To over 1.6 and times the 10 and negative 10, right? Okay, so the unit has been transferred into the GE voltage, right? Understand now? Okay, remember? Okay, and you explain to me why I use the formula.
Because E equals mc squared, so the mass times c squared, and then convert into the units of giga electron volts. So 1 giga electron volt equals 1.6 times 10 to negative 10 joules. So if convert from joules to electron volts, then is over 1.6 times 10 to negative 10.
Okay, choose what? Choose which one now.
C.
Okay, no problem. No, I understand. Okay, remember. Okay, and for 9, the option on. Okay, it's the D, no problem. And how about 10? A 10 answers A. Okay, no problem. And the 1 mark. What is the gravity, right? Okay, it's the wear point to act on it. And here's the 4 marks. Okay, first use what? This one, and then greater than, right? Okay, no problem. And for this one, to show what? Show that is what is the. Okay, no problem. Here's the length. Okay, you use the formula, right? Okay, write down this formula, dot 1 mark, and separating another, and final the value. Final the value. Okay, and this one. There's the maximum speed for the car to stay on the curved part. So they're doing what? What motion? What motion? Circular motion.
Yeah, circular.
Circular motion. Okay, so first you must refer to this one, centripetal force, right? Okay, so what force provide the centripetal force? Friction, right? The 1 mark. And only maintain the circular motion with a certain angular velocity. Okay, another mark. And if this angular velocity too large for the friction, the centripetal force cannot maintain the circular motion, and the car will leave. Okay, no problem. Okay, and this one. To show that the velocity. Okay, no problem. And the force is the 1 mark. Final. Explain why the outcome of the race is difficult to predict. Okay, here's the 3 mark. Here are 3 marks. Formula as the increase. The radius increases and the velocity increases since the maximum value of the force is constant. Okay, it's constant. The car further out to have the higher maximum velocity. But the distance needs to be traveled to longer. Okay, the sentence is right. Okay, because the inner lane covers a small distance, right? Understand? Yeah. Okay, and we know, according to the graph,
Yes, how does.
the inner lane also has the smaller radius of the curvature, right?
Yeah, smaller radius.
Okay, no problem. Okay, understand. And for this one, the graph, and we know. The other one asks to explain why here is suitable. as the model, as the model, as the model, why the heel is suitable as the model. Okay, there are 3 marks. Another mark is 1. Okay, no problem. Relationship, 1 mark. Right. This topic. Describe the result of the alpha particle discovery experiment. Okay. So we're going to explain the majority, okay, and the corresponding result and conclusion, the 1 mark, and the sum alpha, okay. Second, small, another, and final. So inches other than the area of large chord. No problem. Understand. Use the RC, right? To sketch the graph and show how the value is coach. The value is
Introducing Grammarly like you've never seen before. Your all-in-one writing essential. Say hello to Humanizer.
Season 4 finale of Invincible just dropped. I put my peepers on it nice and early this morning. I got up real excited, and I gotta let you know I wasn't let down. I thought it was a really strong finale to a very strong season. But I'm gonna rip the band-aid off right now. I'm not gonna sugarcoat this. Grip your chair right now, sports fans, because it's about to get spicy. The animation blows major ass. I don't think anyone's surprised to hear me critique that aspect of this show. And I understand, I've heard the cope about why it's so stiff and bland because of, how tight the schedule is to get it out, that kind of thing. I understand that, and not wanting to work the animators to the bone in order to meet the deadlines. I get all of that. So then, let's play ball with a little thought experiment here. What if we don't have it come out on such a strict timeline and give the animators more time to flesh it out to make it look even better? I am not someone that needs the jingling keys at all moments of a show. A lot of my favorite shows are slow burns. Invincible is not that. Every episode of Invincible, basically, has action. So when you have an action-heavy show where the action looks like action figures colliding in this weightless fucking of nothing, it's jarring and feels underwhelming, taking the wind out of the sails of a show that carries so much momentum through extraordinary writing. But since they like to have everything in an actual physical fight, when it stands out like this for being really not great, it just kind of sucks. Like PNGs floating around. There are multiple moments in Season 4 that are reminiscent of fucking Garu sliding down the hill in One Punch Man Season 3. And honestly, if this show wasn't so action right up in your titties at all times, I wouldn't care as much because the writing is so strong and I'm really invested in this world and its characters. But with every episode basically having fighting in it and it looks this bad, it stands out a lot and it becomes a big eye-rolling moment. And I know everyone likes to shoot spitballs and bukkake on episode 4 of this season, the one where they go to hell and it feels like filler. That is the most egregious example of it, but it's not just reserved for that. Pretty much all fights, every time they clash, looks like that, save for the key moments. And this is where it shows that they have the talent, they have the ability to make beautiful animated fights and these incredible, breathtaking sequences. They save that for the most pivotal moments, like Conquest Round 2, the fucking remix, or Nolan and Thrag, or really just everything with Thrag getting involved there. Which I get makes sense from their budget and timeline to focus those resources there to elevate those moments because they are so important and it is a huge fight moment. But because it's used so seldomly in the season, it just lets you know what could have been if they decided to actually, maybe pump the brakes a little bit on the cutthroat release schedule and let the whole season get this treatment. It would make everything so much better, in my opinion, and I would personally be fine with a longer wait in between seasons if the entire season can look like that, or look like how it did in Season 1. I praised the animation in Season 1 right when Invincible started. I thought it was beautiful. I thought they did a great job with all of it, and apparently that took 3 years to do, so I understand that might not be feasible, and that is a much longer wait in between seasons, but surely there's got to be a Goldilocks zone in here somewhere in the pipeline where you get great animation and a timely-ish release where it doesn't, just fucking fall into the Stranger Things category of everyone forgetting about it in between seasons. My point is, this show is an incredibly good show. I love Invincible. I think it is captivating. I think it is so fucking strong. But I am constantly let down with the animation now because it just seems to get progressively weaker. So I would just love if that could be spruced up a bit to get back to its former glory of animation quality or something at least closer to it. But anyway, I don't want to harp on that too long because I do have a very positive takeaway from this season. I was very, very entertained. As I said, I'm very invested in the world and the characters, and I think Season 4 gives you so much to chew on because it brings in, I think, the most interesting character, which is Nolan. Omni-Man is doing everything he can to try and atone for his sins, but this show doesn't just flip the switch oh, he's a good guy now, so we all have to forgive him. It plays with this very complicated character and this very messy man as he's battling his own demons and trying so desperately to prove that he has changed. But with his whole family devastated by what he's done, no one can trust him, and everyone's afraid of him. It is so well written that it's not just this instant switch that gets flipped where everyone's okay, we love Nolan now, see how great he's doing, let's all pat Nolan on the ass, all right, let's go suck a fart out his butt, Nolan's a good guy now, yeehaw. They put him in his place, let him know what he did is fucked up, and that he probably will never be able to actually get forgiveness for it. And Nolan's
9, right?
Yeah, the time constant.
Okay. It's right. The scattering experiment. Okay. So we're going to explain the majority, okay, and the corresponding result and conclusion go 1 mark, and the sum alpha, okay. Second, small another, and final. So integers other than area of large chord. No problem. Understand? Use the RC, right? Just sketch the graph and show how the values go. The value is 9, right?
Yeah, the time constant.
Okay. It's right. There are 3 marks. Initially and capacitor. Initially, capacitor and graph potential. No, what? The value is what? The value.
I forgot.
Okay. You need to label the value of the B, remember? Because this is the horizontal, right? The maximum value. Okay. Understand?
Wait, how to label?
To calculate the value is what? According to this, okay. So calculate the value for the potential when the time is 30, corresponding the voltage is what? According to the graph above. Think about it.
8 volts.
Approximately reach to 8, right? Maybe 7.5, right? Understand? Because there's another second, right? Reaches 8. Understand? So you can take the 7.8 or 7.5, right? Understand?
Okay.
Okay. And another use the time constant. The times the formula you use it right, but the time is substitution is 4, right? This one. Why your answer is different from the mark answer? The right answer T is the 5.6 times 10 negative 3 seconds. Why your answer has a difference? There you calculate the wrong answer. Think about it. Why the answer is the 5.6, not the 3.6 millisecond? Oh, the RC is what? It's 9, right?
Yeah.
The RC is 9. But the topic choose the RC is not 9. Approximately. Take the 3. The value is what? This value is what? It's what? 3.3 times what? 7.2, 2.7?
2.7.
And times the 1 point. 3.3 times the 2.7. This part is what? Is the
Oh,
R.
plus. It's supposed to be plus.
Okay, so I can understand this one. The time, right? The times the multiplication. There must be the plus, right? Because this is a series. Okay, understand?
Yeah.
No problem now. Okay, so the RC time constant RC is not right. Okay.
But the answer is still 9 milliseconds.
Not a 9 millisecond. They only label the RC, give 1 mark, not give the value mark. Understand? So I mean, in question A, the mark, the one of the mark of the 3 marks, okay, only gave the RC, the formula, not the value. Understand? So the question A, we don't need to calculate the value, and in the question B, we needed to calculate the value RC. Understand?
Okay. Then how to calculate?
Your answer the 9 must be wrong. So the total R, the total, okay, in the question B, the R total equal 3.3 plus the 2.7, okay, is the K and times the 10, okay, understand? So the value is 6, okay, and times the 10 is 3, okay, over, right? Understand? Okay, so the time constant, RC, now take the value, is the 6 times the 10, right? Okay, times what? The capacitance is what? 1.5.
1.5.
Okay, now the value is 1.5 and times the 10, negative 4, 6, okay, so the value now becomes what? Becomes 9, right? Understand? Now second, okay.